Welcome back to the Deep Dive.
Great to be here.
So this is the show where we try to take that absolute fire hose of information you see in the AI landscape.
It is a flood. Yeah.
And we filter it, we refine it, and we really try to distill it down to the pure technical gold you need to, stay fluent in the field.
And today's mission, I think, is a really critical one. We're doing a 2025 year in review, but we're specifically not talking about the surface level stuff.
Right. No hype about, oh, this model is 1% better.
Exactly. We are taking a deep dive into the technical details, the implications of advancements that have fundamentally altered the entire landscape. We're talking about the architecture, the optimization pressures, the whole engineering recipe for how you build an LLM today.
And that's really the key insight, isn't it? When we looked at all the sources for this year-end wrap-up, the big story wasn't about scale anymore.
Yeah.
It was about methodology. The whole recipe for building a state-of-the-art LLM, just great. It changed completely. It moved away from simple imitation.
And toward this structured, really aggressive optimization.
So we've isolated 6 major technical shifts. 6 conceptual paradigm changes that really define the field right now.
And we're going to unpack all of them, from the core training loop right out to the end user application. We'll get into the engineering constraints, the how behind these capabilities, and the why these changes actually matter at a technical level.
Our promise, as always, is to cut through all that noise and get straight to the critical decisions that engineers in the trenches are making right now.
Yeah.
So let's just jump right into it. Shift number 1, the one that completely redefined the training landscape. The rise of reinforcement learning from verifiable rewards, or RLVR. Okay, so to understand RLVR, let's first unpack the computational context. If you look back, say, to the beginning of 2025, there was this very stable, proven production recipe for building an LLM.
Right, there was a standard playbook.
But it was already showing some pretty critical signs of strain.
That's right. The standard stack, it was 3 major stages. And it had been the industry gold standard since, 2022? Post-instruct GPT. So first you had pre-training, that massive, data-hungry general training phase where the model just learns syntax, semantics, its basic world model.
And that was always the huge computational sink.
Always. Then came the alignment steps. First one was supervised fine-tuning, or SFT.
Right, where you take that big generalist model and you fine-tune it on really expensive, high-quality, human-curated examples to get it to follow instructions.
But even then, that SFT data was, it was limited. It was human bias.
And expensive.
So the final piece was reinforcement learning from human feedback, RLHF. This used human preferences to train a reward model, and that reward model then guided the final policy.
But here's the crucial technical detail, the thing that was becoming the bottleneck.
Yeah.
The computational budget for both SFT and RLHF was always thin.
Very thin. It was a tiny fraction of the total training compute. You could only get so much high-quality human feedback before the signal just got noisy or super expensive, or you just hit diminishing returns.
So you end up with this deeply optimized, massive pre-training phase.
Yeah.
But it's followed by 2 really shallow fine-tuning phases that are computationally almost insignificant.
Exactly. The model was spending 90% of its resource budget learning to imitate text, and maybe 10% learning to align and refine.
And the industry needed a way to apply deep, intensive optimization pressure after pre-training.
Not just during it. And that's where 2025 introduced this technical bolt-on that very quickly became the new de facto major stage, reinforcement learning from verifiable rewards. RLVR.
Okay, so what precisely defines this new stage? Technically, what separates it from RLHF?
The distinction really comes down to the reward function source and its reliability. RLVR is all about training LLMs against automatically verifiable rewards in specific environments.
Or think deterministic domains.
Exactly. Complex math theorems where you can computationally check the proof, logic puzzles, code generation tasks that you can compile, execute, and get a definitive pass or fail.
The key is that the reward is coming from an objective computational environment, not from a subjective human preference.
Right, and that immediately lets you scale. SFT and RLHF were completely constrained by the human bottleneck, which is slow and it's noisy.
But RLVR, with these objective reward functions, it just shatters that constraint.
Precisely. Because if the LLM output solves the math problem, the reward is verifiable, it's immediate, and it's super high fidelity. And crucially, this reward function is non-gameable.
Right. You either solved it correctly within the rules or you didn't.
And that technical reliability allows for just vastly longer optimization runs, We are talking about RL training that consumes compute that was previously reserved only for the massive pre-training phase itself.
That's the huge shift in resource allocation. We didn't stop debating whether to make models bigger. We're still doing that. But we started trying to make them smarter through these intensive, targeted, computationally deep optimization loops.
The compute shifted from just sheer statistical learning to algorithmic refinement.
And the key technical outcome here, this is where the science gets really fascinating.
It is.
The LLMs started to spontaneously develop strategies that look, to us humans, exactly like reasoning.
And this isn't reasoning that's been injected by, feeding it chain of thought prompts in the SFT data. This is strategy emerging organically, structurally, from that aggressive optimization pressure.
Can you elaborate on what those strategies look like? Because spontaneous reasoning sounds a little theoretical. What's the mechanism?
Now let's ground it. The DeepSeek-R1 paper is a great example.
Great.
What did the model actually develop? It learned to structure its own internal operations. So instead of trying a complex multi-step calculation all in one go,
It breaks it down.
it breaks it down. It spontaneously learns to create intermediate calculations, manage those results in its context window, like a little working memory, and then stitch them all together for the final answer.
And if that final output fails, the reward check.
This is the amazing part. The model spontaneously learns complex strategies for error recovery.
So it's tracing back through its own work.
Right.
Like an internal rollback or a debugging loop to find the faulty step and then trying again.
That's exactly right. It's learning to manage a complex state space during a multi-step operation. And the reason this is so new is, well, we could always prompt a model to ask it to reason with chain of thought.
But we were basically just hard-coding a human method onto it.
Right. In the old paradigms, it was incredibly difficult to mathematically specify what the optimal reasoning traces and recovery procedures should even look like for the LLM's architecture.
With RLVR, you don't have to tell it how to reason.
No, you just tell it the ultimate goal. Achieve this verifiable reward. And the architecture, through deep optimization against that objective, finds the most efficient, structured internal path. The algorithm that works best for its own neural weights to maximize that reward.
It's a self-discovery of algorithmic structure. That's a fundamental change.
It moves it beyond just statistical imitation into something that really does resemble active, structured planning.
And this technical capability leads directly to a massive compute shift and new scaling laws.
Yeah.
I mean, if RLVR offers extremely high capability per dollar, a much better ROI for complex tasks than just making the pre-training data set a little bigger.
The money follows. The financial incentive dictates the architectural shift.
Labs started diverting huge amounts of compute away from those marginal pre-training gains and into these longer, deep RL runs.
And this introduced a powerful new control knob and an associated scaling law, which is, I think, maybe the most important engineering development of the year.
The knob that lets you control capability as a function of test time compute.
Exactly.
The idea that you can increase intelligence on demand by just injecting more compute at inference time, that's revolutionary.
In practice, it means you can scale the model's thinking time. You tell it to generate longer reasoning traces internally before it gives you an answer.
So you're running it through more internal steps, letting it self-correct, or maybe generate multiple parallel solutions and then pick the best one.
Right. The capability is now scaled not just by the static parameters, the model size or training tokens, but by how long you let it run its internal iterative processes when you ask it a question.
More compute at test time equals a better result.
And there's a predictable scaling law that governs it, which emerged directly from that RLVR optimization.
And this is what made the difference feel so intuitive to users. OpenAI's O1 model in late 2024, that was the first demo, right? It had hints of this.
It did. But O3 in early 2025, that was the clear inflection point. That was when you could reliably give it a complex, multi-step technical problem like generate and test this block of Python code that older RLHF-only models would just fail on 90% of the time.
The difference wasn't just the final answer. It was the structured, durable process that got it there.
And that structural shift in training, it leads us directly to our second major technical paradigm change.
Which is this conceptual realization that LLMs are not evolving animals.
No. There's something fundamentally different. The source material calls it summoning ghosts.
And this shift is so important for engineers who are designing systems that rely on these models.
It is. We have to discard those comfortable biological analogies, evolution, growth, generalized intelligence, because the technical stack is completely, totally divorced from biological reality. We have to understand what we've actually built.
And the difference is rooted in that optimization pressure we were just talking about.
That's the core contrast. Human neural nets. They were optimized over millennia by the messy physical pressure of tribal survival.
Right. Finding food, avoiding predators.
Exactly. Reproduction, navigating a chaotic world. LLM neural nets are optimized for these hyper-specific synthetic goals.
Imitating all of humanity's text.
Collecting maximum reward in a deterministic math puzzle.
Getting the most upvotes on LM Arena.
Exactly. So if the optimization objective is synthetic, digital, and hyper-focused,
the resulting intelligence can't be this generalized, robust thing like a biological mind. It has to be an artifact of its specific training.
Which is why the most striking technical manifestation of this is what we now call jagged intelligence.
And this explains why their capabilities are so wildly uneven, which causes huge architectural headaches for people building apps.
Let's talk about the technical basis of that jaggedness, because it links right back to RLVR.
It all comes down to verifiability.
Yep. Because RLVR, our most powerful optimization tool, requires verifiable domains, environments with objective, computationally generated rewards. The LLMs are just overwhelmingly optimized in the vicinity of those domains.
So the neural network learns these incredibly powerful, deep, complex strategies for things like code, formal logic, complex math.
But what about the messy, subjective, non-verifiable domains?
Like common sense, or social reasoning, or interpreting a weird, ambiguous, real-world situation.
There are no strong, objective, scalable reward signals for those things. So on those messy domains, the model is mostly relying on the statistical imitation it learned during pre-training. It can be competent, sure, but it lacks that deep, structured optimization from RLVR.
So capability spikes only where that intense, objective optimization pressure has been applied.
And the technical outcome is that amusingly jagged performance characteristic. The model can be a genius polymath in, say, advanced differential equations.
For generating super efficient Rust code.
And at the same time, it can display the social and cognitive limits of a confused third grader when you ask it a basic common sense question.
And that confused third grader is, as the source puts it, seconds away from getting tricked by a jailbreak to exfiltrate your data.
Exactly. Because its safety guardrails, which are mostly based on the shallower RLHF, haven't been aggressively optimized to the same depth as its reasoning capabilities in those verifiable domains, so that jaggedness means your system design has to account for these unpredictable, catastrophic failure modes outside the optimized zones.
Okay, this idea of jagged intelligence, it provides the perfect technical context for what happened next in 2025.
The benchmark crisis.
The complete and utter loss of trust in our established benchmarks. And this isn't just about cheating. It's about architectural incompatibility.
Right. And this is where we need a neural signal check. Here's why this development actually matters at a technical level.
So what's the core issue?
The core issue is that benchmarks, from old ones like MMLU to newer code and math tests like GSM8K and Human Evol, they are, almost by their very construction, verifiable environments.
They have a known, computable, deterministic right answer.
And if they're verifiable,
they are immediately susceptible to that powerful new tool we just discussed, RLVR.
Or even just targeted synthetic data generation designed to mimic those RLVR environments. And so the industry process of benchmaxing became, well, it became rampant. And technically, it was unavoidable.
So LLM teams, they're driven by the leaderboards, and they inevitably start constructing these specialized optimization environments.
Sophisticated RLVR loops, synthetic data, all of it designed to be adjacent to the exact pockets of the embedding space occupied by the benchmarks.
So they're not training for general capability anymore. They are actively growing those capability jaggies, specifically to cover the surface area defined by the benchmark tests.
It's a localized, targeted optimization for a single metric. It became so technically sophisticated that the source calls it a new art form. Training on the test set is a new art form.
Which means LLM engineering now explicitly includes this strategic process of creating proxy environments just to elevate scores on public leaderboards.
And this leads to a fundamental technical decoupling. Benchmark performance no longer reliably indicates actual generalizable capability in the real, non-verifiable world.
Let me pressure test that for a second. If benchmaxing is so rampant and performance is so jagged, why hasn't a major lab been publicly called out for releasing a model that clearly fails outside of these optimized benchmarks. What's the real-world engineering trade-off they're making?
They're betting on the utility of the optimized domain itself. A model that is a phenomenal, verified coder is incredibly valuable on its own, even if it can't debate philosophy.
So the benchmarks measure success in a closed system.
Perfectly. Crushing all the established benchmarks looks like perfect optimization for the narrow domain of standardized, verifiable testing, but it fundamentally lacks the robust, generalized, transferable skill set you need for real-world complexity, which is often non-verifiable.
The benchmarks are measuring optimization success, not general intelligence.
Right, and this forces us to confront a really fundamental technical question. What does it look like at a purely technical level to crush all established benchmarks? To get near-perfect scores on tests designed to measure intelligence and still clearly fall short of AGI.
It looks exactly like the ghost.
Exactly. A system that's superhuman in its specific optimized domain, but brittle and childlike everywhere else. The benchmarks provide a false sense of security about generalization, and it forces application developers to build these increasingly complex layers of error correction and guarding around the model to manage its inevitable failure outside that verifiable zone.
Okay, let's move on to our third major shift. We're transitioning now from the core model training architecture to the application layer.
Right.
And the meteoric rise of applications like Cursor, especially in coding and developer tools, it demonstrated a key technical revelation.
The necessity of a new, thick LLM app layer.
Cursor wasn't just some simple UI skin wrapped around a generic GPT-4 API call.
Not at all. It showed that to get high reliability and depth of function, you need a significant amount of complex engineering sitting between the user and the foundational model.
And that layer is thick because it's solving problems that the foundational model, even an RLVR enhanced one, just can't solve on its own.
Let's break down the 4 technical functions that define this new layer, based on the sources. Function number 1, and maybe the most technically challenging given context limits, is context engineering.
This is so critical. The app layer performs this intelligent, high-level management of the limited context window.
Yeah, the foundation model might have a 200,000 Cambro token limit, but a modern codebase could easily be 5 million tokens.
So the app layer has to do intelligent retrieval, summarize the relevant parts, and structure all that data into a maximally useful prompt dynamically, in real time.
It's not just dumping raw code into the context. It's acting as a smart preprocessor and information curator.
Making sure the right context is there at the right time.
Precisely. Function number 2 is probably the most computationally intensive: orchestration.
Right. These apps aren't just making one API call to the flagship model.
No, they're orchestrating multiple LLM calls, and they string them together into these increasingly complex directed acyclic graphs, or DAGs.
We're talking about a multi-stage process. Model A makes a plan, Model B does the search, Model C refines the output.
And Model D self-critiques the result. The app layer manages that entire interconnected workflow. And critically, it's also responsible for the technical optimization of that DAG execution.
So it's carefully balancing performance and cost trade-offs in real time.
Exactly. The app layer intelligently decides, should I use the cheapest, smallest model for this simple summarization task? Or do I need to reserve the expensive, flagship RLVR enhanced model for the critical reasoning step?
That balancing act managing latency, throughput, cost, that is a complex application-specific problem that's solved entirely by the app layer, not the foundation model.
Then you have functions 3 and 4, which are about user interaction, providing an application-specific GUI for specialized tasks, and offering an autonomy slider.
That autonomy slider seems like a direct response to the Jagged Intelligence problem we just talked about.
It is. How much rope do you give this smart but occasionally very confused ghost? The app layer provides the interface to technically control the degree of agency.
This all leads to the verticalization implication. The debate in 2025 was basically settled. Foundational labs, they graduate the generally capable college student.
The broad, smart, generalist model.
But it's the LLM apps that take that college student and turn them into a deployed professional in a specific vertical: legal discovery, pharma research, software architecture.
And this is where the technical differentiation happens, creating that thick layer of value. The app layer organizes, fine-tunes, and animates these models into true specialists.
And it does that by supplying critical technical components that the base model just can't access during its general training.
Let's focus on those components because they are the technical inputs that differentiate the app layer. You've got private data, sensors, actuators, and feedback loops.
Right. Private data gives it specialized domain knowledge. Sensors let it perceive the world beyond a text prompt. Actuators let it take action.
Commit code, modify database, start a transaction. But the feedback loops are arguably the most crucial engineering component.
Because these loops let the model learn from the success or failure of its actions in that specific vertical environment. It's a kind of real-world closed-loop reinforcement learning.
Way beyond what the foundational lab could ever provide during generalized RLVR training.
So the app layer is where the model goes from being a passive text generator to an active, specialized participant in a closed-loop system, creating real, persistent value.
And that concept of actuators and feedback loops brings us neatly to the rise of the true LLM agent.
Demonstrated most convincingly by Claude Code, or CC. And this wasn't just a new model. It was a shift in where that intelligence physically lives.
C was the definitive technical demonstration of a convincing, modern LLM agent. Its defining characteristics were that computational persistence, loopy behavior, and the ability to string together tool use and structured reasoning for really extended problem solving.
It could sustain an objective over a long time, iterating, self-correcting, moving through complex states.
Yeah, unlike the early single-shot models. But what made CC a true paradigm shift wasn't just its agency. Other models were kind of hinting at that.
It was the localhost paradigm shift.
Exactly. The agent ran locally on the user's computer, accessing their private environment data and context directly.
And this was a stark technical contrast to the early agent efforts from labs like OpenAI.
Right. Their efforts were all focused on cloud deployments, running agents inside these remote, containerized sandboxes orchestrated from a web UI like ChatGPT, a remote brain talking to a simulated environment.
And the argument for the localhost approach is purely technical and architectural. In our current reality of slow takeoff and jagged capabilities, running the agent on the developer's machine just makes way more sense.
It does, because the agent needs robust, consistent, low-latency access to the specific environment it's trying to manipulate. A developer's machine is a unique, deeply configured, complex thing.
And trying to replicate that whole environment with all its weird permissions and tools inside a remote cloud container is computationally expensive, messy, and slow because of network latency.
You're basically saying that local access simplifies the whole context engineering problem we talked about before.
Right. The model doesn't need to be told the environment state. It can just read the environment state with almost no overhead.
Exactly. And when the agent fails, which it will because of jaggedness, the cost of iterating, of debugging its actions is dramatically reduced because that feedback loop is local and instantaneous.
That low-latency, high-fidelity feedback environment is critical for the agent to learn and execute its loopy, self-correcting behavior effectively. And this really needs a neural signal check. The true distinction. We have to emphasize that the primary distinction is not just about where the AI ops run, cloud versus local, for some regulatory reason.
No, the location is secondary to the technical access it grants.
So what's the decisive technical advantage?
It's the immediate low-latency access to the already existing and booted-up computer's essential elements. We're talking about persistent access to the OS's installation paths, the complete runtime context, local data caches, secrets, configuration files.
Everything. So if the model needs to know precisely how Python 3.12 is configured on your machine with all its environment variables,
it just checks the local path. If it needs to access a specific API key stored locally in a secure config manager, it has that path. This is fundamentally different from passing some limited, sanitized snapshot of the environment through a restrictive API call.
And that direct, low-latency interaction with the actual working environment is what unlocks the agent's full potential in a complex dev setting.
Anthropic understood this. They packaged CC into this really delightful, minimal command line interface, a CLI. They recognized that for advanced users, the fastest path to interaction is text-based integration with their existing shell.
Which defined a whole new interaction paradigm.
Yep. It's not a website you visit, like Google or ChatGPT, which implies this synchronous, separate interaction.
It's this little spirit or ghost that lives on your computer.
It's resident, it's persistent, and it's deeply embedded. It's always ready, and it can monitor or interact with your operational environment with minimal overhead.
For professional use cases like coding, which requires constant, tiny adjustments to the local machine state, this form factor just fundamentally changed what continuous AI interaction looks like.
It's a technical necessity born from the need to manage the complexity and brittleness of jagged intelligence in a real-world environment.
our fifth technical paradigm shift, which is, it's intrinsically linked to the rise of these local agents and the RLVR-driven code capability we've been discussing.
Is the concept now universally known as vibe coding?
2025 really was the year we crossed the capability threshold. It became possible to create genuinely impressive, functional, efficient programs just from high-level English instructions.
The ability to essentially forget that the underlying code even exists. That abstraction reached critical mass.
The term vibe coding started as a joke.
Yes.
You just give the model a vibe of what you need, and it delivers.
But it stuck because it perfectly captures the conceptual shift. Programming is no longer strictly reserved for these highly trained, specialized professionals who know every bit of syntax minutia. It's becoming something that anyone with a good conceptual understanding can just delegate.
This also ties into a broader technical trend, which is the democratization of high-cost skills.
That's a great point. LLMs kind of reverse the historical diffusion of technology. Usually, new, deep tech benefits big corporations and government R&D first. But LLMs benefit regular people significantly by democratizing access to complex skills like programming.
But vibe coding has this crucial twofold technical impact that goes way beyond just being a consumer novelty.
Yeah.
Yes, it empowers regular people to program, but it also massively empowers trained professionals to write so much more software.
Specifically, the software that would otherwise never have been written.
Exactly. Think about the old constraints on a professional engineer. The cost of development. The 3 days spent coding, debugging, testing was a huge barrier.
So if you needed some specialized utility that would take 3 days to hand code but only served a 1-hour diagnostic purpose, the ROI was negative, the project was dead before it started.
And vibe coding completely changes that economic calculation because the cost of creation approaches zero.
It does. Let's look at a technical example from the sources. Vibe coding a custom, highly efficient BPE tokenizer in Rust.
Rust is notoriously complex.
It is. Normally, an engineer would just grab an existing, battle-tested, off-the-shelf library to save the massive development headache.
But if you can instruct the agent to instantly generate a highly efficient custom version, optimized specifically for your unique dataset or hardware, why use the standardized library?
It unlocks performance gains, tiny microseconds, a reduced memory footprint that were previously inaccessible because the manual development cost was just too high. The engineer can now optimize for performance, not just convenience or time to market.
And the idea of vibe coding entire ephemeral apps just to find a single bug is maybe the most radical technical change.
It treats code not as a long-term asset, but as a disposable utility.
Which is the core realization. The malleability of code. Code is suddenly free, ephemeral, malleable, discardable after a single use.
If a bug is elusive, instead of spending hours manually stepping through code, you just tell the agent, vibe code me a custom monitoring daemon for this specific API call that reports its payload size.
You run it once, find the bug, and delete the tool. The cost of creation is near zero.
And this technical reality is going to fundamentally terraform software development workflows. The engineer's role shifts away from writing boilerplate
and towards defining the complex high-level system architecture and just refining the vibe, the objective function for the LLM to execute against.
The value moves definitively from implementation details and syntax mastery to high-level conceptualization, system integration, and critical quality control. The LLM is the implementation engine. The human is the architect and verifier.
Okay, for our final paradigm shift, let's turn to the necessary evolution of the user interface itself.
This leads us to the technical significance of projects like Nano Banana and the future of the LLM GUI.
And the overarching conceptual frame here is so critical for understanding where we're going.
We have to frame LLMs as the next major computing paradigm. Think of them like the mainframe or the early personal computers of the 70s and 80s.
And when a new paradigm emerges, it almost always starts by favoring the machine's modality.
In the 70s, interacting with a computer meant typing commands into a console. Pure text.
And today, chatting with an LLM is structurally the exact same thing. Text is the machine's favorite format. It's the native format of the LLM's weights and its input tokens.
But here's the massive architectural and user experience disconnect that has to be solved. Text is not the favored format for the person.
Not at all. Humans are fundamentally visual and spatial consumers of information. We don't like reading dense text. It's slow. It takes a lot of cognitive effort.
Our brains are much better equipped to process spatial relationships, diagrams, immediate visual cues.
Which is precisely why the graphical user interface, the GUI, was invented for traditional computing.
It was invented to bridge that massive gap between the machine's favored format, the text command, and the human's favored format, visual, spatial, intuitive interaction.
So the technical challenge for LLMs is crystal clear. The paradigm won't be complete until they adapt to human preference.
The LLMs should communicate to us in our preferred format. Images, infographics, interactive dashboards, dynamic slides, entire web apps.
Markdown and emoji are just. They're early primitive versions of trying to dress up raw text to make it easier to look at. They're not enough.
No. The true next-generation LLM GUI requires more than just formatting text. It needs a unified, multimodal, generative experience where the model can fluently articulate its thoughts spatially, not just sequentially, in a text stream.
And this is where Google Gemini's Nano Banana demo enters the discussion. The source is cited as the first powerful hint of what that true LLM GUI might look like.
It demonstrated the capability to instantly generate and iterate on complex visual artifacts that were tied directly to the conversation's context.
So what's the technical significance here? Beyond it just being a really high-quality image generator, we've had diffusion models for years.
The key technical insight is that the paradigm shift is not just about the image generation component running as a separate service. It's about the joint capability that results from having text generation, image generation, and world knowledge all deeply tangled up and coherent within the same model weights.
Okay, so the system doesn't have to output a text plan, then make a separate API call to an isolated diffusion model, and then try to stitch those external outputs back together in a pipeline.
Right, that pipeline stitching, it introduces technical friction, latency, coherence errors. The true advantage of the Nano Banana approach is integration. The intelligence that can vibe code a custom BPE tokenizer is the same intelligence, in the same model weights, that can immediately generate a complex labeled diagram to explain how that tokenizer works.
Or a slide presentation for its rollout. No external calls, no context switching.
And that unified multimodal capability where world knowledge and the ability to articulate that knowledge in different modalities are deeply integrated, that's what will eventually drive the creation of intuitive, dynamic, spatially organized LLM GUIs that will finally supersede the simplistic chat box we rely on now.
The chat interface, our current gold standard, is really just a historical artifact.
Yeah. It needs to be superseded by something more natively human-focused, just like the console interface gave way to the mouse and the desktop metaphor decades ago.
Wow. What a profound and rapid year of technical change. Let's just quickly review the 6 paradigm shifts that really redefined the engineering landscape of 2025.
We started with RLVR, reinforcement learning from verifiable rewards. That completely redefined model optimization by shifting compute from general pre-training to this deep objective fine-tuning, which forced the emergence of algorithmic reasoning.
That structural training shift led directly to the emergence of Jagged Intelligence, the realization that LLMs are ghosts with these unpredictably spiked capabilities, which immediately compromised the reliability of our traditional benchmarks.
Which just became targets for benchmaxing?
Right. Then we discuss Cursor and the rise of that thick, necessary LLM app layer, which supplies all the critical technical components, private data, sensors, actuators, feedback loops, to animate those generalist models into reliable, deployed professionals.
Then we saw Claude Code define the true LLM agent and establish the localhost paradigm, leveraging that critical, low-latency access to the user's own booted-up environment, which is just architecturally superior for managing brittle, jagged agency.
We examined vibe coding, the crossing of that capability threshold that makes code free, ephemeral, malleable, and discardable, fundamentally terraforming the engineering economics of making software.
And finally, we looked at Nano Banana, which gave us the first concrete hint of the unified multimodal core that's needed to create the true LLM GUI, the necessary evolution from the text-based console we're using today.
The pervasive feeling from 2025, I think, remains really complex.
Yeah.
LLMs are simultaneously a lot smarter than we expected.
Thanks to deep RL optimization.
And a lot dumber than we expected.
Thanks to that inherent jaggedness. But in any case, they've become an indispensable, highly leverageable utility.
The consensus among our sources really argues that the industry hasn't realized anywhere near 10% of the potential of our current capabilities, even before we start considering the next generation of foundational models.
Right. Despite all the rapid progress we've just reviewed, conceptually, the field is still wide open. There are so many architectural and optimization ideas left to try.
We're holding a paradox then. We believe we're going to see rapid, continued progress.
And we believe there is a ton of fundamental work still to be done. So considering the jagged intelligence of these ghosts and the rapid progress we're seeing from these verifiable optimization pressures, here's a final provocative thought for you to consider, aimed at the technical constraints.
Which current core LLM limitation, not addressed by the 6 paradigms we've discussed, so not reasoning depth, not context length, not interface modality, which one is the most crucial technical hurdle that needs a completely new optimization pressure to overcome?
Think about what fundamental human capability is still missing, and then think about what kind of objective, scalable, and verifiable environment would you need to build to train a ghost to acquire that missing piece of intelligence.
Food for thought on the future of fundamental AI research. Thank you for joining us on this deep dive into the technical shifts of 2025.
To stay updated on the latest in AI and ML, visit our webpage, neuralintel.org, and check us out on YouTube. Until next time.